Swayam Prabha. Digital India. Educated India.
There was a element and we had 3 MPa here, 15 MPa in y axis. So let me draw the axis also, x and y, and we had 2.5 I think in this direction. You just let me know if I'm wrong. So we had 3 MPa in x direction and 15 MPa in y direction, right? That was our problem. Now, how do I draw this Mohr circle? Now, if you remember, we have to first draw the 2 axes. This will be our normal stress axis, and this will be our shear stress axis. And we will grade the same way. Now, since you are saying it is 15 and 3, so we can go by 3, 6, 9, 12, and maybe 15. So this will be same as 3. This is positive 3, and this is negative 3. And if you remember, I told you the clockwise was negative and anti-clockwise was positive. Okay? So in a graph paper, you first do this. Then we have 2 plane, one let's say A plane and another let's say B plane. Now in the A plane, you have to tell me what is the value. So the normal stress is 15 MPa, and whether it is positive or negative, I should take. Who can tell me? The shear stress, it will be positive or negative at A plane?
Positive.
Positive. So I hope everybody understood, because this is going in a counterclockwise. So this is positive. So this one is 3 and negative. Okay. So these are my 2 points in this graph paper. I'm going to plot that. So first one is 15 positive. So somewhere here is my point. And another is 2.5 negative. Somewhere here is my point. So you draw the line and it will basically pass through 9. Okay. And then I mark it. This is my A plane and this is my B plane. So this particular plane become a point in the Mohr circle. Okay, Mohr circle of stress. Now this is my center, and from this center I will draw a circle considering the radius of this much. So let me see whether I can draw a better circle. Okay, so that become my the Mohr circle of stress. This is not the best circle probably you have seen, but for this purpose I will accept it. Okay, now so this is the angle. This completes your Mohr circle of stress. That's it. Now if you remember, your sigma 3 was 2.5. This is this point, and this point was your sigma 1, and this was your sigma 3. Now if you ask me that what is the angle from the x-axis, now you can see the x-axis is towards this A, because the A plane is in this case orienting towards x-axis. So this is the angle towards sigma 1. So you measure this angle, whatever you get, you divide it by 2. So if this comes as 2 theta, So theta is the angle where you rotate from x-axis to sigma 1 axis. Okay, and your problem was, if I remember, it was rotated 30 degree. So if it was rotated 30 degree, then you will rotate 60 degree. So this must have come somewhere around here. So that was our basically the plane when I gave you that problem. If the 30 degree rotated, and as a result, you are seeing this become negative. The shear stress become negative in this, in that problem. So this is how we basically draw the Mohr circle. Now you see, many things it comes. Now, what is the center of the Mohr circle? Can anybody tell me? The center of the Mohr circle is?
Sigma xx plus sigma yy by 2.
Yeah, sigma xx plus sigma yy by 2. Okay. Now, do you remember what is N1, invariant of stress? Do you remember that? I gave you N1 and N2. The N1 was this.
Sigma xx plus sigma y.
Correct? So this is basically, that's why it is invariant. So in a Mohr circle, the center is one of the invariant of the stress. So it doesn't matter which plane you take. This every point is a plane, right? Because here all point is a plane. So it doesn't matter which point you take, center doesn't change. That's why it's invariant. Now what is other one?
Determinant.
What is the other invariant?
So determinant.
Yeah, but now you in a circle, what could be other invariant?
So the radius.
Radius.
The radius. Yeah, and if you see, the N2 is nothing but the radius. Okay, you can manipulate it, and it will come tau xy square minus sigma xx into sigma yy. Okay, so that you can manipulate. You know the radius here. The radius r is nothing but that one, square root of 1/4 sigma xx minus sigma yy entered square plus tau xy square. This is the radius. Now, if you this is also invariant, you have to apply this. You have to apply this one to get that second invariant. This is also constant. So when you apply, you'll see that N2 is also constant. So basically, the two invariants is nothing. One is center, the another is radius. Okay. Now you can, if you consider 3D, then it will basically, it's little complicated, but we are not discussing here. So you got how to plot a Mohr circle in 2D. That's why I'm saying there is a 3D Mohr circle also. Okay, 3 circle will come, but we are not discussing this in this class. So I hope this clears your doubt, if any, regarding how we draw Mohr circle, how we interpret it, and how we get the data from Mohr circle. Okay. Now I will go to a thing of whether if I can draw Mohr circle of stress, can I draw Mohr circle of strain? The answer is yes. We can also draw Mohr circle of strain. Only thing you have to remember when you are drawing Mohr circle of strain, everything is same. Only thing, just a minute. This gamma xy, when you are using this gamma xy, this will be replaced. Okay, this is coming from basically 2 tau xy. See, we have shear stress in both the planes, but you remember when we have calculated gamma xy, then I told you this is theta 1 plus delta theta 2. So basically 2 tau xy combinedly is giving me 1 gamma xy. So wherever is tau xy is given, you will replace this by this only tau xy, you will replace by gamma xy by 2. So the axis will become gamma xy by 2, means gamma by 2. I can take it out, gamma by 2, and this is epsilon n. So this is the normal strain, and here it is gamma by 2. Other everything remains the same. Okay, all, even in each formula, what I gave you, if you want to convert this into strain formula, you can convert. Only thing you have to remember, it is gamma by 2. Okay. So this is how, at this point of time, you just remember that if you have to draw a Mohr circle of strain, sometime we do that. Then the tau xy or the tau term will be replaced by gamma by 2. Otherwise, you will be making a mistake. Okay. This is just, you have to remember when you plot Mohr circle of strain. Now quickly, I give you a problem on strain, since we are on that. This I have also added in the class note, I think, as an exercise. This is also available in the book, so I am getting it from the book. Let's say this is a thin plate and made with steel. This is x and y axis. This dimension is 0.5 meter. This dimension is 1 meter. And let's assume this is A, B, C, and D. So this is a thin plate. We are considering 2D only. This is the dimension. Now, because of the stresses, what happened is this has deformed like this from this point on. This is the same point. So point C becomes C star. And the coordinate of C star, I can give you, coordinate of C star is 0.502, 0.996. Okay. So previously it was 0.5 and 1, and because of some kind of stress, some normal, some shear, you can see that it has, both the thing has applied. So coordinate C becomes C star, and all other coordinate remain the same wherever it is. Okay. I hope you understood the problem. Now you have to tell me what is epsilon xx, epsilon yy, and gamma xy at point C. What is this value? Okay. You have some knowledge of, deformation, maybe from your JEE course, but here we can apply the concept which is given before. So let me solve it for you, so that subsequently whatever the problem given in the exercise, you can do it by yourself, or they will help you in doing in tutorial.
Sir, the Asari Dinesh was he's raised his hand. Might be he's having question.
Yeah, go ahead. You ask your question.
Sir, no, sir, nothing, sir.
Nothing.
It's,
Right?
by mistake it will be.
Okay, fine. let me do it, then maybe you will have some questions. Let me use the blue one. Okay. Now, what we are seeing here is very simplistically, if you see, at point A, B, and D, there was no deformation occurred. So deformation occurred in CD and CB line, you may call, or you may call it plane also. So in general, I'm not sure whether you know something called Pascal's triangle. Like if I want to write the displacement U in X direction, displacement U, so I can write it some A0 plus A1X plus A2Y plus A3XY. Okay, so this is coming directly from Pascal's triangle. Now, what is that Pascal's triangle? 1 x y, then x square, xy, y square. I think you have studied that. Now, since it's a quadrilateral, so we normally take these four. This is called quasi-linear, deformation. The quasi-linear because there is a nonlinear term of both of them are order 1, and they are pure nonlinear term of order 2. So we are not taking them. So we are taking this additional nonlinear term, the xy term. And why this xy? Because we are clearly seeing there is a shearing has occurred. Because there is a clear shearing has occurred here. Okay, some sort of shearing has occurred. So we are seeing that, and this is that shear component which will come from this xy term. So these Pascal triangles we will be using, but again, if you see very closely, we can also prove it very quickly. Let's say I take at U at A, the displacement x direction deformation at point A. This is basically 0. And this 0, and if I now plot it, if I now put the xy value, so you are saying this given A0 is equals to 0. Because x is 0, y is 0, and xy will be 0 at point A. Since it is 0, so A0 will be 0. Similarly, you will find this one will be also 0 if you plot it at point D, and if you put it at point B, you will see this is also 0. So actually, this U is nothing but my some A3XY. Using the Pascal's triangle, so we found a relationship between displacement or the deformation in X direction with the coordinates. Similarly, because it's a more or less symmetric, the V we will be write some B3 XY also. Okay, so this is my governing equation or the primary equation, the variable, how the deformation has occurred in this. So this you have to understand from the figure. Okay, so this is what has happened, and we always fall back this Pascal's triangle. Okay, you have studied that, and these are all applications of those Pascal's triangle. So now if I know this is the relationship, okay, I can very well now apply my relationship here. So this now I have to just use at point C. Now at point C, this is given. What is this value given? Can anybody tell me? What is the U at point C?
A3Y
0.002, and this is positive. Okay, this is positive or negative?
Sir, positive.
This is positive. See, It has tension or compression. At point C, this has come out, right? So it is pulling. So my normal stress may have been pulled it in this direction. That's why it has come out. So in our case, we will consider it negative because it is in tension. You can also take positive. Later on, it will become negative. But you have to write that this is in tension. So that's why I am writing it negative. From very beginning, you can say that this is negative because it is in tension. Okay. And at B, what has happened? The deformation in Y direction. This is positive, right? It has compressed. So this 0.004. Everybody agrees? Where from I am writing this? So this is 1 minus 0.996, and this was 0.502 minus 0.5. So now these two values are known to me. What is the value of X and Y at point C? The value of X is 0.5, Y is 1. So I can quickly find A3 is minus 0.004 and B3 is plus 0.008. Okay. So once I got this, then what is epsilon xx? Del u del x. And this is nothing but A3y. So A3 is now known and Y is 1 at point C. So this is nothing but minus 0.004. Epsilon yy is del V del Y, which is V3x. So this one will become 0.004. Okay, this is the strain. And if I take gamma xy, this will be del u del y plus del v del x. So del u del y is A3x plus B3y. So you can put the value and you can get the strain tensor at point C. So like that you can get at any point. Just then we have to give you the point, what is the value. So first we are establishing the relationship between U and V using the Pascal's triangle. In this case, we are considering the quasi-linear because there is not much complicated. See, nonlinear, what I am trying to tell you, if this one was getting something like that, this one was getting something like this, okay, or this, it has become, the plate has become something like that, then it is nonlinear, okay. So this has, it has not happened like that. So if nonlinear term, then we could have gone to okay. Now the extension of this also I can give let me just delete this part and redraw that. Let's say now I know the strain tensor at point C. Now if I ask you, okay, what will be strain tensor in this direction then at point C? At point C, the strain tensor along the CA line. Can anybody tell me what will be that? or how to find that out? See, I now know this. Epsilon xx here, epsilon yy, and gamma xy is known to me now. Now, can I find out what is the value in this direction?
Yes, sir. We will find the angle of that line and then take the components of epsilon xx and epsilon yy.
Right, not component. You have to use that transformation matrix which I gave you before. Okay, that's c square epsilon xx plus a square epsilon yy. Then I think cs gamma xy, and the angle is known to you. Clockwise, this much. Okay, this is the angle. So this is 90 degree plus whatever theta here. You can find. It's very easy to find the theta because this, you know, this is 1 and this is 0.5. So you can find the theta. Somebody has to mute your, yeah. Okay, so once we know, then we can determine the strain at any direction. That's absolutely no problem. Okay, so in your tutorial, there will be several, in the book, several questions are given. So I'm sure they will ask you to solve at least one problem from there, so that you know how to calculate the strain tensors when deformation is given. Okay.
So I had a doubt, sir.
Yeah, go ahead.
So I didn't understand how did we get those functions u and v from Pascal's that triangle you told by putting other terms zero, sir. How did we get that?
Oh, see, in Pascal's triangle is 1 x y x square xy y square. Let's say we do not have to go beyond that. Now, if I have to write any function in here, let's say the function ui I want to write. So in generally we write this multiplied by a coefficient. Each one will be multiplied by a coefficient, right? This is how we form a equation. Now I want to keep as a quasi-linear, not non-linear. So this will be 3xy. I will only take these 4 terms. Okay, because why 4 terms? Because this is basically rectangular and also I have 4 points given. And it shows that it is basically linearly, it has deformed linearly. If it has shown non-linearly, then I could have taken non-linear. And then more data point would have been given to me. Okay. Since there is only 4 points, so I can have only 4 coefficients. So you have to match that. This is the number one thing. Now you see at point A, my x and y is 0, 0. So if you put at 0, 0, so this is u equals to a0. So u at A is a0. And this value is 0 because it didn't move. There's no deformation here. So this automatically becomes 0. Now you try at B. U at B. So I will put a0 is 0. So a1 into 0.5. This is 0, y is 0, and this is also 0. And this is also set 0. So that means this is also 0. Right? Similarly, you will find this is 0 at point D here. The A2 will be 0. So only thing surviving is this. And it is showing that it has basically, we have applied mostly the shear here. We didn't apply any pulling for this particular deformation to occur. Just shearing is applied, and that is the reason it has pulled this. So, but you don't have to know that at this point of time. During the math, what do you have to know? That how to apply the Pascal's triangle to write any equations. Any polynomial equations can be written by Pascal's triangle. Okay, in 2D and 3D, or in for that matter any ND also. Okay, so but you so far know 2D or 3D. Is that clear? Or some doubt?
Yes,
Hello, sir.
yes, sir. It's clear, sir.
It's clear, right?
Thank you, sir.
Okay.
Hello, sir.
Yes, sir.
Yeah.
Sir, if the shape of the that seat will be pentagon, then what equation we have to consider?
Same equation. Now you have to just tell that how many are fixed and how many further component you have to take. Let's say you have to take x square. Okay. Then if pentagon may not have deformed linearly. It may not be. So they will give those 5 values. So maybe the x square term has to be taken or y square term has to be taken. Okay. So accordingly we choose that how many, depending on the problem, which term to choose and which term not to choose. That problem definition will tell you. Okay, that's why it becomes little tricky, depending on the geometry. But you can take any polynomial and then you put those values wherever the point the value has been given, and then it's automatically will come. Okay. So you do not have to worry for those kind of geometrical shape. Okay. Now I go to another topic that is still I'm in strain. That is also a very important aspect. It's called volumetric strain. At this point of time, you just know the definition. When I go to next chapter, the stress strain relations, this is very important. The question becomes, when we are deforming a body, let's say a 3-dimensional body, we have applied certain, let's say this is a 3D body, X, Y, and Z direction. And because of the normal stress only, there is no shear acting, only normal stress. This body becomes, its size changes to this. Okay. So either it may shrink or it may enlarge, but the shape will not change, only the size. Okay, that means we have played with its volume. Okay, directly. So in that case, the volumetric strain we normally write epsilon V is the change of volume, that means delta V by the original V. And volume change in rock mechanics is very, very critical. There are some material where the volume change is very high. Let me give you an example of like gold. Can anybody tell me why gold is so popular? Give me 2-3 reasons. Very quickly. Number 1.
Because it can be easily molded into any shape.
Okay, that's good. Okay, you have told the, the difficult one first. And another?
Cost, sir.
What? Now cost, that's different issue. It is shiny. Okay, it is very shiny. But the gold is popular because what he said, it's a what we call the ductile material. When I will come to that, I'll tell you. Even you see, using a 5-gram gold, they made a earring or something very beautiful, 2-piece of ornaments. And if you take 10 gram, you can make a locket, and so many design they do with just 10 gram. You think, and you can make that gold, that 10 gram, a long wear. So you can play with its volume like any different ways. the any other material it gives which is close to basically silver. Silver is another which comes close to gold, and another material is copper. That's why these three basically this material are very, very important in that sense. And because gold is also shiny and it is kind of a rare earth mineral, also means it doesn't found everywhere. That's why the cost and everything comes into picture. But we can make beautiful ornament because it's a ductile material. I will come later on. So this volumetric change it can be very, very high. You know, this can be 50%, 60%, or even 100%. We can change the volume. For the same mass, we can change its volume. So, having said that, how do we calculate it? So, delta V by V is the change of or the volumetric strain. So, let's assume it has some original length. This is Ly, this is Lx, and this is Lz. And let's say now the change, what has happened here is here, let me use another color. Then this change, what has happened is, let's say delta Lz, and here it is delta Ly, and there it is delta Lx. So I can write V as Lx, Ly, and Lz. And the change of volume, this is nothing but V minus delta V. So this one is change in volume is V dash, and that one will be Lx minus delta Lx, and so on. Ly minus delta Ly, and Lz minus delta Lz, right? So this is the change of volume. So okay, so what we are getting now, we'll be doing this 1 minus V dash by V. This is what we will get here. And let me delete that so that I can get some space. So now if I put it there, so you will see I'm getting 1 minus, this is minus, so del Lx by Lx, and 1 minus del Ly by Ly, and 1 minus del Lz by Lz. Now, can anybody tell me what is this?
So partial change.
Yep, that's basically epsilon xx, right? 1 minus epsilon yy and 1 minus epsilon zz. Okay, because it's the normal strain, there is no shear. Remember that. There's only normal stresses are applied. So now if I do that, this will come something like epsilon xx plus epsilon yy plus epsilon zz and plus some quadratic term. And plus 1 cubic term, right? Means you can see the last term will be epsilon xx, epsilon yy, and epsilon zz when you do. Okay. And this will be quadratic, epsilon xx into epsilon yy, something like that. So this, I told you before, this is in the order of 10 to the power minus 3 or 10 to the power minus 4. The quadratic term will be then in the order of 10 to the power minus 6 or minus 8. cubic term will be in the order of 10 to the power -9 or -12. So definitely these all terms are very, very small as compared to this. So we can put it 0. That means the volumetric strain is nothing but summation of 3 normal strains. Okay. So you remember that the volumetric strain is nothing but the summation of 3 directional normal strain. Okay. So this is how volume changes. So when you are giving a stress to a 3-dimensional body, the volume does change. Remember that. Okay. And this change of volume is depending on its material properties. Different material react differently. Okay. Not all material is gold. That's why gold is so priceless. Okay. If all material could have been like gold, then gold would have been just like another material. Okay. Like coal. You just give a little bit of force and it will crumble. Okay. There is hardly any ductility in a piece of coal block. Okay. Similarly, granite, or let's say the glass, it's a highly brittle material. Okay. It doesn't change volume that much before it fails. Okay. So those we call the brittle material, and gold we call the ductile material. Okay. So this we will use in the next chapter, how to calculate it from a testing data and all this. Now, next thing I want to tell you about a very important issue in solid mechanics, and the solid mechanics is basically resting on this principle. It's called the equilibrium equations. I'm sorry, what I went, got it. Like equation of stress or stresses. The equilibrium equation or stress equilibrium equation. Okay. See, so far I have discussed considering a block where there are stress sigma xx and sigma xx. Okay. Then I also told you that sigma xx or any tensor is basically a coordinate dependent. If you change the coordinate, this will change. So none of you have asked me, sir, then what happened here? You didn't change the coordinate. If this coordinate is 0, what is the coordinate here? Is it the same coordinate or it is different? If it is different, the stress should have been different here. Okay, because our sigma xx is depending on the coordinate. So, and this is absolutely right. So that means this big, square block I have drawn, this is nothing but a dot, a point. Okay, just we have enlarged it, thousands time maybe, just to show that this is a block, but both direction stresses are same. Now, what happened if this is a finite distance? Okay. Now, what happened if this is a finite distance? What kind of equilibrium equation we can write then? So let me first draw with a finite distance. Let's say this distance is dx and this distance is dy. So my coordinates still x and y, and I have applied a stress sigma xx here. Definitely now, since there is a finite distance, I am saying here, this will not be sigma xx. I'm writing the equation first, then I will explain it to you. This plus del sigma xx del x dx. Now, I'm sure you have done differential. Some of you may be already understanding how it has come, but let me test your knowledge a little bit of differential, which you probably also done in your higher secondary. Let's say I have a curve here. This is a function fx. Let's say y equals to fx, and this is x. Now, if I know at some x, if I know the value f or y, if I know this value, at this x, I know this value. Do I know the value at dx distance apart? So if I know fx, do I know fx plus dx? Or how do I find that out?
By Taylor's theorem.
What?
Taylor's theorem.
Taylor's theorem, correct. So Taylor's theorem is one. So I can truncate the Taylor's theorem. This is one way, or if you just use simple, derivative, the application of derivative. What I will do, I will draw a tangent here. Basically, Taylor theorem in 1D, 1D means, sorry, in 1 degree is basically what you have done in your higher secondary. So if I draw a tangent here at this point, and then I draw this, let's say this tangent is dy dx, right? This tangent will be dy dx, okay? And then if this is dx, so what will be this dy? This will be dy dx into dx, because this is dx. So in your higher secondary, you have done this is differential, you have written is del, this is also you have written del, and you have said if I have to find out a delta y, then I have to make a slope dy dx, multiply with the del x, and this is how I find the differential. So this is exactly the same. Or you can find from the Taylor series expansion. This is the first order. You do not consider the higher order term. You ignore the higher order term. This is the same thing. Okay. Now here the del came because this is the partial derivative. Sigma xx is, this is the function of both x and y. So that's why it will be partial derivative. So I hope everybody understood how I have written that. Now I will write the other. So this one is, if I write sigma yy, this one will be sigma yy plus del sigma yy del y dy. If I have a tau xy here, and this tau xy, I will write tau xy plus del tau xy del y dy. If I have shear stress here, which is also, let's say, tau xy, and this one we will write tau xy plus del tau xy del x dx. You can see the difference because it's in the x direction. Okay. So you see, this is the what will be the stresses in that particular element of dx and dy. Now, since I have given a finite a dimension, so any material will have its gravity, at least it has a density. So if it is a density, it will have a body weight. So that body weight may be acting downward. So I write it By, the body weight component. It's meaning that its density they multiply by the g, which is the acceleration due to gravity. And let's say to make it complete, there is a something in dx or in the x direction also. So I have a By component, which is acting, let's say, downward, which is due to gravity, and let's say for completeness, I also have a in x direction. So now what I have to do? I have to balance the forces in x direction. So I'm just doing one. Rest you will get in book of the second equation. So if I now write the equation in x direction, you can see this is sigma xx into dy. Here there is sigma xx plus this thing. So if I do it, it will be minus del sigma xx by del x dx dy. This is one force, because this will cancel out. So, and in the negative direction we will get this. That is in the x direction, this one tau xy and this. So similarly, I will find minus del tau xy del y dy dx, because it is apply on the dx plane. This tau xy. And I have this body force component, which is minus bx, and this is per unit volume or per unit area. So this is 0. So this is the equation in x direction. Similarly, I can write in the y direction also, or you can also write. Now I can delete this, this one, I can delete this, I can delete that, also this, I can delete this also, I can put plus. So what I got? Del sigma xx by del x plus del tau xy by del y plus dx is 0. This is one equation. Another equation will be del tau xy by del x plus del sigma yy by del y plus by is 0. These two in 2D in Cartesian coordinate system is called the equilibrium equation of stresses. Okay, this is very, very important equation. Similarly, in 3D, I have three unknown: sigma xx, tau xy, and sigma yy. I just do not know these three terms, and they are function of x and y. But I have two equations. Can I solve it? I'm sure I cannot solve it. Okay. But what it is saying to us, that sigma xx, sigma yy, and tau xy, they are probably not so much independent to each other either. Okay. So they are not independent to each other. And also, the way the equation has been written, I think you have solved differential equation, I'm sure, but you have only solved one differential equation at a time, not two differential equations simultaneously. I'm sure you have not solved that. So solution of this equation is also not so easy. Okay, but it's already given. People have already worked on it and already published and given in the book also. In my book also we have given the solution of this equation. So this what we call, you remember this equation, this is called the equilibrium equation of stresses or the stress equilibrium equation, and everything starts from here. You are now sitting on a chair, it follows this particular equation. Any solid material will follow this equation in static loading. Okay, in static loading. I will come to maybe dynamic later on. But what I will do now, whatever time left, I'm not sure whether time we have. Oh, we are already over the time. But you can do very quickly, or I can give you a problem very quickly. You can solve it in your home. Let's say this is a ceiling and a steel rope is hanging like this, having density rho and having length L. Let's say this direction is y direction. You have to derive an equation sigma yy equals to, which is a function of rho L and y. This is the fixed here. The rope has a density rho. So what is the normal stress developing at any point here? Maybe you can consider the y from here, y equals to 0 at here. So at any point, or you may consider y here also going up, it doesn't matter where you consider y. Okay. So you have to derive an equation where sigma yy is a function of rho L and y. So you do that. Tomorrow we will again come, and if you have already solved it, is very good. If you don't, I will.
Rho density per unit length.
Rho is the density, kg per meter cube.
Okay, sir.
Kg per meter cube. Rho is the density per meter cube. Okay. So you derive an equation. It's very simple. You can do it from your JE Funda also. I can guarantee it. Okay. And you can also use the equation I gave right now. Okay, using that also you can do. I will do it using that. So today we stop here, and again tomorrow we'll come back at 10 o'clock.